Hello everyone, myself Sudhanshu Kumar from IIT Indore. In this session, we are going to continue our legacy of organic named reaction series. And today, we will talk about Corey Nicolaou macrolactonization reaction, that is a name reaction. The name is just based on the scientist who discovered the reaction. Okay, na? Generally, in the organic chemistry, you will see the name reaction, the name given on the basis of a scientist who discovered that reaction. So today we are going to talk about Corey Nicolaou macrolactonization. What does mean this word? Macro means what? Lactonization means what? Okay, and Core means what? And Nicolaou means what? Okay, so here macro means large. Okay, macro means large here, right? Macro means here large, right? And here lactonization means the formation of a ester. Ester. Lactone means what? Ester, no? Here lactonization means formation of a ester. Formation of a cyclic ester. Okay? Lactone means what? Cyclic ester. So here it's a macrolactonization, formation of a large cyclic ester. Okay? Here means large ring here. Okay? Large ring. Large ring. Okay? So here and Kore means what? Kore means it is the name of a scientist. That is the Ise Kore. Ise Kore, I hope you all know this scientist, Ise Kore. Okay, and one more scientist who discovered this reaction, Nicolaou. Casey Nicolaou. Necolaou. Okay, so these are the two scientists who discovered this reaction, Ise Kore and Casey Nicolaou. Okay, in the year of 1974. Okay, in the year of 1974. In the year of 1974, these two scientists contributed this novel reaction, this novel method to prepare the macrolactonization, means large ring lactone. Okay, so basically what happened, I want to give some brief about this reaction, background of this reaction. So basically in the year of 1970, if you see 1970, before 1970 there is no method. Okay, there is no general method to prepare the medium and large ring lactones. Okay, no general methods to prepare the medium and large ring lactones. Okay, large ring lactones from highly functionalized. I will tell you what does this mean. Okay, functionalized hydroxy acids under mild condition. So basically what happened before 1970, okay na? Before 1970 there was no such general method to prepare the medium and large size lactones from highly functionalized hydroxy acid. This is our hydroxy acid. Okay, that's why in the 1974 these two scientists has contributed to this reaction, to this new reaction, Corey Nicolaou macrolactonization. So now we will see what they have done in this reaction, what is the reactant, what is the reagent, and what is the product. This is our product of this reaction, cyclic ester, that is a lactone. Because here we can see here is a bracket writes here n. This n means what? This n you can take 1, 2, 3, 4, any integer value, either greater or equal to 1. Okay now. or it can be 0 also, okay. So that's the method of a preparation of a large ring lactones, okay. And this is our reactant, here is a hydroxy acid, and this is our reagent here, these two are the reagents, okay, these two are the reagents. Now see the mechanism. So first of all, when we do this reaction, we take these two reagents, okay, and and we do the reaction between these two only first, okay. So here this is our reagent, first reagent, and this is our second reagent. So here we have phosphorus here, ppH3, and because phosphorus having a lone pair here, and because here is a SS bond, and this bond is a very weak bond, and that's why this phosphorus will wants to attack on the sulfur and wants to break the ring, okay. When the phosphorus lone pair will attack on the sulfur, then what happen? Then this SS bond will break as a S negative, as a S negative, okay, and this negative will take the H plus from the solution, okay. Now this is the formation of another product here like this, and one we got this, right. When the phosphorus attack the lone pair, phosphorus lone pair attacking on the electrophilic site of a SS bond, okay, this bond will break and we got these two products. Now after that, here the phosphorus got a positive charge because phosphorus has donated their lone pair to sulfur. That's why phosphorus is got here positive charge. Now this will act as an electrophile. This is our electrophile now. This is our electrophile. Now what happened? Now what happened? See, now the role of a reactant will come. Now the hydroxy acid will come in this reaction. So see here, and this is our electrophile. This is our electrophile, and this is our reactant. We can see here this oxygen having a lone pair. Just do the delocalization and it will attack on the phosphorus, and now the bond will break, okay. So after that you will get something like this C double bond OH, this C double bond OH here, you can see C double bond O like this, okay. This is your C double bond O, right, this one, and this is your, when the oxygen is attacking on the phosphorus, it's formation of a bond, not single bond. So here is a OPPH3 bond, right, and because this group leave, okay, so there is no such group here, okay. So this is all about this step, and after that this group will come again here, role, and here the sulfur having a lone pair, and this lone pair of sulfur, and because this CO group is a electrophilic position, because CO having a delta positive and delta negative charge, electrophile, electrophilic position, and here we having a sulfur is a nucleophile, and that's why here is a delta positive and here is a delta negative on the oxygen, and that's why the sulfur lone pair is attacking on this C double bond O. So you will get something like this, the bond will get shift here, and after that you will get something like this one. Now what happened, because here bond has shifted on the oxygen, you can see that O minus, so here the O minus, and you know that in the organic chemistry the PO bond is very strongest bond. PO bond is very strongest bond in the organic chemistry, and that's why this is the driving force of the reaction here, the formation of a PO bond, and that's why here the O negative charge will get come back here, and now this POPH3 will leave, and this is the driving force of this reaction, driving force of the formation of a PO bond here, okay. That's why the reaction is occurring like this, okay now. So this is the driving force of the reaction, formation of a PO bond, and we got here POPH3, okay. So after this one more got you like this here, here's something like this. If you just attack here to here. You want to go here to here. So here it's a nitrogen, like this, sulfur, and here we have a double bond O. Okay, here it's the OH, and here you have a delta N here. Okay, so this is the same. We have this product. Okay, these two and this one are same. Okay, now what happened? See, because you have here OH now, OH here. Okay, a hydroxy acid here, OH group, and you know that OH group, OH hydrogen is a acidic, right? OH hydrogen is a acidic. This H is a acidic hydrogen. Acidic H, right? Acidic H plus. Understood? So that's why what happened? Now this lone pair nitrogen will take this proton. Okay, intramolecular proton transfer. Okay, and after this you will see here NH positive charge, because the nitrogen is taking a proton from here, because this proton is a acidic proton. That's why you got something like this intermediate. Okay, now what happened? Now because this N has taken the proton from the OH, now it's become O minus. And now this O minus will just attack on this carbonyl center, this one, this electrophilic position, intramolecular attack, electrophilic position. Okay, after this it will attack on this electrophilic center. You got like this one. Okay, and now the bond will shift here on the oxygen, like this. Understood? This is the intramolecular attack. Okay, intramolecular attack leads to formation of a ring here. Okay, so after the intramolecular attack you will get something like this. Understood? Clear now? Here up to here it's clear, I think. Yeah, after this, see what happened. Because this negative charge is attacked at the CO bond here, so that's why the pi bond of the CO bond will get delocalized, get shifted on the oxygen as a negative charge. So here it's our negative charge, right? And here it's something interaction, you can say hydrogen bonding here. Okay, now between NH and O minus, you can see that there is a H bonding here. Okay, and this O negative charge will get come back, because nitrogen having a positive charge, it wants to be a neutral, and that's how it happen. Just O minus will get come back, and this bond will get shift here, and this bond will get shifted on the nitrogen as a negative charge. Now we got our product. So this is our lactone. Cyclic ester. And this is your byproduct, that is a 2-pyridine thione. Okay, this is our major product. This is all we want. Okay, this is all we want from this reaction. So this is all about the mechanism of this reaction. In such a way, you can get here macrolactonization. This one. Now let me recall one more time very fast. Okay. Now this is your nucleophile. It will attack on the SS bond. Bond will get break here, taking a H plus from the solution. You will get two product here, but here phosphorus having a positive charge. That's why it will work as a electrophile. And here we having a reactant here, hydroxy acid. Now this will come in the role, and this oxygen lone pair will get delocalized here and attack from this oxygen, because this oxygen is localized. That's why this oxygen attack is possible. Okay, here the bond will get break. Now you can see here something like this, and because this molecule will again come here and attack on this electrophilic site CO bond, and now what happens? This bond will get shifted on the oxygen as a negative charge. Now after this, because nitrogen here is a lone pair is a localized, and this lone pair is a basic, and that's why it can take a proton from this OH, this H is acidic. Okay, now you got something like this one, and because here O minus will get come back, and because the driving force of the reaction is the formation of a PO bond, because PO bond formation is a strongest bond in the organic chemistry. That's why this is the driving force to do this reaction in such a manner. Now after this is the H bonding interaction here, O and H. Now this O negative will come back here, and this bond will get break, and this will get negative charge on the nitrogen, and you will get here two products. One is the lactone cyclic ester, that is our main product, major product, and this is our second byproduct, that is a 2-pyridine thione. Okay, so this is all about the Corey Nicolaou macrolactonization. Okay, so you can take a screenshot also if you want. I'm just scrolling slowly. You can pause the video and think about the mechanism step by step, why this is happening, why this not. Okay, you can ask your question to yourself. Okay, so if any doubt, let me know in the comment box. I will try to resolve all the doubts, okay, to all the comments. Okay, and we have a special group here, Telegram group. The link is given in the description box. All the notes, PDF, all will be provided in that group. Okay, so please join our Telegram channel. Okay, and please subscribe our channel, Chemistry Portal for more videos of chemistry related, organic chemistry especially. Okay, so thank you so much. Bye bye, take care.